So, first things first. Today we are going to start this video differently. If you think you are strong today, pause this video right here and answer these questions that you are looking at. This is Trig grade 11. Nevertheless, these are not all the questions that we are going to work with today. It's just a sample of what we are going to do. These questions do not cover all the topics we are going to do today. This is just a sample again of what we are going to do. So let's get to the introduction. So guys, welcome back to Manala's Arc. I hope you are all well. I've realized that I've created a lot of videos that are revision videos, test revision type of videos, and I didn't have a lot of content videos whereby I'm actually introducing the content to you. So this video is meant for that. This is not a revision video. This is meant for us to go into detail about some concepts that are in the topic of trigonometry. So this is part 1 with all the topics that you see in this page. At this point, we are going to cover all these topics today, and it will still be part 1. Afterwards, I'm going to do the second part of this video with components that are meant for part 2. But everything that you see here today, it's meant for part 1. For those who are wondering why my voice is so low today or on this video, it's because I'm recording this video so late. Look at what time it is. Let me refresh that. Look at what time it is, guys. It's 2 a.m. in the morning. So obviously I can't be that loud, guys. It's still too early in the morning, right? I woke up this early just to make this video for you. Okay, so let's get to it. Right, so where can we start? Let's see. In grade 11, guys. Oh, by the way, in case if I forgot to say it again, welcome back to Manala's Arc. I hope you're all well, and I hope you'll enjoy this video. Okay, so now what happens is that in grade 10 we covered a few basics about trig, and I'm going to browse quickly through those basics, right, to save us time. So we know that we have trig ratios, right? Trig ratios. What are those trig ratios? We have a cosine, we have a sine, and we have a tangent. Right, what is a cosine? These are the first 3 basic trig ratios. A cosine, we write it as a cos, so it must be a cosine of something. A cosine doesn't exist alone, it exists for an angle, right? It's a cosine of something all the time. You cannot just have a cosine on its own. And then we have a sine, same thing applies to a sine. And then we have the tangent. So in short, this function we write them as cos, sin, and tan. Right, and then after that we have the inverses of this function. So in total we have 6 trig ratios. We have the basic 3 and their inverses. So you have 1 over the cosine. This we call this the what? The secant. To write that we write sec of theta, right? And then we have 1 over the sine. 1 over the sine, we call it the what? The cosecant. How do we represent the cosecant? It's cosec theta, right? Cosec of something. And then we have 1 over the tangent. How do we refer to this one? It's the cotangent. How do we write this one? It's the cot of theta. See how beautiful is that? Now we have 6 trig ratios. You all know that by now. And then where do we use these trig ratios? We use these trig ratios on last year, or in grade 10, we used these trig ratios on right angled triangles, right? And then we said on those right angled triangles, this time instead of labeling this side, this hypotenuse side, instead of labeling this side AC, we said we know that we can label this side based on the angle that it's opposite to that side, but with small letters. So this is a small letter B, and then this side it's called what? Small letter A, and this side it's called what? Small letter C. So now, instead of saying the line AC, we just say B. This side, it's called side B. And then here, instead of saying the side BC, we just say A. And then here, instead of saying the side AB, we just say C, because it's opposite to this angle C, right? And then afterwards, we said we have things like, again, on the same right angle triangle, let's put this. We said that we have unknown angles. A way for us to represent unknown angles, we use things like theta, we use a letter like beta, we use a letter like alpha. Most of the times, these letters, they represent unknown angles. So how much is this angle? I know this angle already. It's a right angle, so it's 90 degrees. But then this angle, because I don't know it, I can represent this angle as theta. And in this angle also, because I don't know it, I can represent it as alpha, right? So these are variables that we use now to represent angles we don't know. Just as much as in algebra, we will represent a number we don't know with an alphabet like X. Now in trig, for the angles we don't know, we represent them with either theta, beta, or alpha. I hope that makes sense. So in general trigonometry, one of the basic things we have to keep in mind, it's the Cartesian plane. Let me draw a Cartesian plane here. So these are just rough sketches. Nothing is perfect here. So on the Cartesian plane, I know I have this side is 0 degrees, this one is 90 degrees, this one is 180 degrees, this is 270 degrees, and when we get back here, this is the 360 degrees, right? Now this is called quadrant 1, this is called quadrant 2, and this is quadrant 3, and this is quadrant 4. I'm still running over the basics now, right? So, and then we have this system, the cast method, cast, whereby C represents the cosine. This represents all trig functions. This represents the sine. Let's say the sine of theta. Let's use theta there. Cosine of theta. Remember, we said a function doesn't exist alone. And then here we have what? The tangent of theta, right? So what do these things mean? Why are we including these things? What are they about? So the thing is now, the cast method is there to help us identify which trig ratios are positive in those quadrants. Make sense? So in this case, it means the only trig function that is positive in the fourth quadrant, it's a cosine. So if we ever find a sine in the fourth quadrant, if we ever find a sine of theta, just note that it's negative. And then if we ever find a tangent in here, just know that it has a negative answer. If we ever find a sine or a tangent, we'll just get negative answers, because only a cosine is negative here. And then here on this one, it says all. So whether we have a cosine of theta, we have a tangent of theta, or we have a sine of theta, it's all supposed to give us a positive. They are all supposed to give us positive values. If you don't get this, don't worry, you'll understand this as we move on. But we did this in grade 10. And then in this quadrant, the third one, we know that the tangent, it's the only one that will give us a positive answer. If we ever have a sine of theta, it will give us a negative answer. If we ever have a cosine of theta, it will give us a negative answer. Same thing applies here. I don't think I need to do this one too. The sine will be positive and everything else will be negative. I hope that makes sense. So now, what happens with what we just spoke about? So here I created a question for you. I just wrote this down. Please excuse me if you can see my handwriting. It says, if 3 tangent of theta minus 4, and theta is an element, or it's an angle found between 180 and 360, determine the value of 25 square sine of theta minus 5 by the cosine of theta, with the aid of a diagram and without the use of a calculator. Now, how do we do that? First of all, when they say when they tell you something like, with the aid of a diagram, you need a Cartesian plane here. This is trig, guys. So since you need a Cartesian plane, what type of Cartesian plane do you need? You need a Cartesian plane that outlines all the cast elements and with the angles. So this is 0 degrees, this is 90 degrees, this is 180 degrees, 270 degrees, and this is also 360 degrees. Right? Quadrant 1, quadrant 2, quadrant 3, and 4. I don't want to write that because it will cause a lot of detail onto my Cartesian plane. So here's the cast symbol. At least we know which function is positive where. Now, what did they say here? They said that our theta is found between 180 and 360 degrees. So it's either our theta is, sorry, it's either our terminal it's in this quadrant or it is in this quadrant. One of the two. It's either in quadrant 3 or quadrant 4. So this part here, it gives us two options whereby our terminal might be in. So, and then we need to use something that will hone down that detail, right? Oh, sorry. So if 3 tangent of theta minus 4 is equals to 0, and then we have this, in which this thing here, it helped us locate two possible quadrants that our terminal might be in. This part now, this part here, it's going to tell us exactly where in those two quadrants is our terminal in. So we take that, we take 3 with the tangent of theta minus 4 being equals to 0, and then we solve for the tangent of theta there. So obviously we transpose 3 tangent of theta is equals to positive 4, and then how do we remove 3 from the function? We divide everything by 3. This now removes that, and I'm left with the tangent of theta being equals to 4 over 3. I hope that is set. Now, what does the tangent of theta compare? It compares the opposite over the adjacent. Right? How do we represent the opposite in trig? It's represented by y. How do we represent the adjacent? It's represented by x. So now, what we know is that our tangent, it is positive because we can see that this fraction is positive. So now we still have to decide whether our terminal is going to be on this hand or our terminal is going to be on this hand. All set? Now, if our terminal is on this hand, on the Cartesian plane, values that go to this side are negative and values that go downwards are negative. If our terminal now it is on this side, let me use a different color. If our terminal is on this side, it means our x value is supposed to be positive and our y value is supposed to be negative. Now let's put that into practicality. So this is supposed to form an imaginary triangle. We are still deciding where our terminal is supposed to be. If this represents the y value on this side, let me put this. Perfect. Now I was saying, if 4 represents the y value, because on this terminal we know that below this y line everything is negative, I'm going to have negative 4 there. And then if this represents the x value, I know that x is supposed to be negative on this side, right? And then I know what? I know that negative 3 over negative 4, it's going to give me positive, negative 4 over negative 3, it's going to give me positive 4 over 3, which is what I have here. Now let me see why this terminal is not true. Let me use a different color there. Hope you can see that. Yes. The reason this terminal is not true, it's because if I have a y value there, my y value is 4. We know that downwards to the Cartesian plane, our y value is supposed to be negative. So I have a negative 4. But then in terms of the x value is on the right side of the Cartesian plane. And I know that all values on the right side of the Cartesian plane for x are all positive. So which means now here I will have something like negative 4 over 3, which gives me a negative fraction, and that is not what we have in this case. Here we have a positive fraction, which only makes sense that I have negative 4 over negative 3, and that's why I ended up with a positive fraction for the tangent of theta, right? So our terminal now, it's there on the third quadrant. So since we know now that our y value is negative and our x value is also negative, we know that this yields to us a positive answer, right? Perfect. So which means now this is my x value, which is, sorry, this is my y value. Let me not make another mistake. This is my y value, which is equal to negative 4, and this is my x value, which is equal to negative 3. Now, if this is supposed to form an imaginary triangle, which is a right angle triangle, it means I must find my r value for me to be able to solve anything. Bear in mind, guys, I haven't started solving the question yet. I'm still preparing myself to solve the question. So let's do that. Now, to find my r value, how do I find r? Using Pythag. I know that r squared is equals to x squared plus y squared on a right angle triangle. Then I give my reason there, Pythag. All set. And then r squared now is equals to, what is my x value? My x value is a negative 3. So I have negative 3 all squared plus, what is my y value? My y value is negative 4. So I have negative 4 all squared. And then to solve for r, I have to put things in the square root now. But the square root, how it is? It's a plus minus square root. So which means, what is 3 squared? It's a 9 plus, what is a 4 squared? It's a 16. Let's put everything under a root. What does this give me? It gives me a plus minus 5, right? And then I get to choose my answer for r. I know my r, that it's a positive 5, and my hypotenuse, it's never a negative value. So I have to cancel that. You see that? So my r, it's a positive 5, and my r can never be a negative 5 because we are measuring r. R is always positive. Now with those details, now I'll get to answer the question. So please cram this r, cram the x, and cram the y. So I erased everything now so that we can get to the part where we answer the question. Do you even still see the question? This is the question. They said determine the value of this thing here. This thing here, the one that looks complicated. This thing here. So let's do that. Let me use a pen. Nope. Let's choose a pen. So it says 25 with a square sine of theta minus 5 multiplied with the cosine of theta. Here what you have to do is, what does the sine represent? What does the cosine represent? So here I have 25, and then in brackets I substitute for sine, and then I square that, minus 5, in brackets I substitute for the cosine, right? So the sine compares what? The sine compares opposite over hypotenuse. How do we represent opposite? With y. How do we represent hypotenuse? With r. So what is my hypotenuse? My hypotenuse, we said my r, it's 5. So here I put 5. And then what is my opposite? My opposite is y. What is my y value? My y value here, it is negative 4. So I put negative 4 there. And then for this one here, I'm looking for the cosine. The cosine compares what? It compares adjacent over hypotenuse. Right. What is the symbol for adjacent? It's x. And what is the symbol for hypotenuse? It is r. Right. So what is my x value? Here it is. My x value is negative 3. And what is my r value? Here it is. My r value is 5. Right there. So from here we just simplify. What do I have? I know that I have to square this, so I still have 25 outside the bracket. When I square a negative, I get a positive, so I don't need to write that. When I square a 4, I get a 16. When I square a 5, I get a 25 minus. I have a 5 there, which can cancel with the 5 there. I have a negative and a negative, which gives me a positive. And then I have a 3 there. So here's a 3. All right. So I have a 25, which cancels out with the 25. And then I'm left with the 16 plus 3 there. I hope you know how to calculate your values, guys, without a calculator. So how much do we get here? We get a 19. So the answer we're looking for here, it's 19. See how beautiful is that? Math is so beautiful like that, guys. Let's get to another question. So here's another one. It says if 2 cos alpha and I'm sure you can read that on your own. I'm just going to get straight to the answer, right? Okay, so to answer the first one, what are we supposed to do there? What are we supposed to do? Let me underline here so that I separate everything from what I'm doing, and then I don't keep on erasing the question by mistake. All set? So let's choose a white color there. Perfect. All right. So what are we supposed to do? They said with an aid of a diagram. It means the first thing here that we have to do is to get the diagram. We need that diagram. Here is the diagram, and then this is 0 degrees. We know that this is 90 degrees. This is 180 degrees. This is 270 degrees, and this is also 360 degrees. Right here. And then we have the cast method so that we know which function is positive in which quadrant, right? And then what else did they give us? Let me use a red pen here. Look at this. This time they didn't give us an interval. They just gave us this thing here with a less than sign. When it says the sign of alpha is less than 0, when people say something like less than 0, any number that is less than 0, we are saying the number is negative. So they are saying here that the sign of alpha is negative. So on the Cartesian plane, where is the sign negative? The sign is negative in this quadrant, and the sign is negative on this quadrant. So one of these terminals is true, and our role now here is to make sure we find out which terminal here is true, either this one or this one, because that's the only point where sign is negative. So here we have this statement: 2 the cosine of alpha plus 1 is equals to 0. So we solve for the cosine of alpha there so that we can see on which terminal is that true. It's to solve for that, we're just going to have the cosine of alpha is equals to, and then I have negative 1 there. How do I remove 2 from cosine of alpha? I divide both sides by 2. And then it says now the cosine of alpha is equals to negative half. So what is this saying? It's saying the quadrant that I must choose between the two, it is the quadrant whereby the cosine is negative. Where is the cosine negative? In this side, the cosine is positive. So which means the quadrant that I'm using, it's this one. This is the right one. All set? Perfect. Let me erase the screen now. So I removed the other terminal that we don't need, the one that was not true here. So now I need to get to the part whereby I continue to answer the question. So now that I know this quadrant, that this is the one that I'm working with, I need to find my x value, I need to find my y value, I need to find my r. This is what I need. I'm using this diagram to find these values. Once I have them, I'm able to answer all questions. So far I see that my cosine of alpha has a negative half, right? Let me remove some things here so that they don't disturb you. Let me remove this. All right. This is what I know so far. What does this represent? This represents an r. So can an r be negative? No. So which means this negative that we see here, it's not for the r. So my r is 2. I know that, right? So what does this negative belong to? It belongs to that numerator there. What is the numerator for a cosine? It's the adjacent. This is x. And this is r. That's what we know, right? So which means my x now, it's negative 2. Does it make sense? Yes, it makes sense that on this side of the Cartesian plane, my x is negative 2. All set. And what do I know about my r? My r is also 2. So my x is, I'm making a mistake there. Small mistake. My x is that 1 there. My x is 1, and my r is 2. So does it make sense for my x to be -1? Yes, it makes sense for my x to be -1. Why? Because it's on the left side of the Cartesian plane, and in the r it's supposed to always be positive. So I hope you're ready for that. So now what do we have? We are just left to calculate for y. So how do we do that? We use Pythag. R squared is equals to x squared plus y squared. Reason for that, it's what? Pythag. Always provide a reason, guys, when you use Pythag. So I substitute here. What do I have? This is 2 squared being equals to, substitute here. What do I have? -1 all squared, and then I'm looking for this y squared. This is 4, this is +1, and I have my y squared. Therefore my y squared is equals to 4 minus 1 that way, which means my y now, for me to remove this, I put a plus minus square root on this side. What is 4 minus 1? That is 3, right? Let me squeeze everything in here. So now what is my y? My y is either positive or negative the root of 3. I'm keeping it there, guys. And then I hope I didn't make a mistake here. Yeah, it doesn't look like there's a mistake. So moving on, and then what happens? I'm supposed to choose my y. My y, it is either positive root 3 or my y is negative root 3. Now which one makes sense here? When you have your y value below the x, below the Cartesian plane like that, is it a positive y or a negative y? And negative y is the one that makes sense, and the positive one, it's not true, because you can only have a positive y above the Cartesian plane. So I have negative root 3. Make sense? Perfect. So here I have negative root 3. Oh, sorry. So now let me erase everything and keep this, because this is all that I need now. So to answer the first question, what do I need? Oh, and by the way, guys, as you see me writing and erasing things, the things that I removed now, it doesn't mean that you don't have to write them on your question paper. Please show all your steps. Show all your steps, because those items are also needed too. They are needed. Show all your steps. Okay, let's move on. So here, for me to actually get to answer the first question, I used this table here. What does the tangent compare? It compares y over r. Sorry, the tangent compares y over x. What is y? My y is root 3. What is my x? My x is -1. This way. Let's put a bracket so it looks neat. And then what does my sine compare? My sine compares y, which is -root 3, over what? The hypotenuse, which is 2. Now when I have it, let's take it step by step. Let me not rush. Negative and negative gives me what? It just gives me a positive. And negative gives me what? A positive 2. It also gives me a positive. So now let's get to solving that. Let me erase this thing here. I don't know how I forgot it. So now we make this to have a denominator of 2. So I multiply this by 2 over 2. So that it can have a denominator of 2. All set? What do I have then? I'll end up having 2 root 3 all over 2 plus root 3 all over 2. Now my denominators are the same. What can I do? I keep one denominator and then I add the numerators. All set? And then when you're looking at this thing now, what do you see there? Well, we see that this has a root 3 and this has a root 3, and we are adding them. So what are we adding? We are adding like terms. When you add like terms, what are you supposed to do? You keep one variable and then you add the coefficients. What is the coefficient here? Coefficient is 1. So I add the 2 and the 1, I get 3, and then I represent them with that 1 root all over 2. All set? That's how you do it for the first one. Here you won, guys. This is a giveaway. So moving on to the next question. What do we have here? We have 2 multiplied by a function, so I'll keep the 2 outside, and then I open a bracket, and then I square the bracket because of that square, right? And then this is supposed to be a fraction. What does the sign compare? It compares opposite over hypotenuse. What is opposite? It's my y value, negative root 3. What is my r, or my hypotenuse? It's 2. Minus, I have the cosine. The cosine is also squared. You see this square there? So I square the whole bracket. The cosine compares what? X over r. What is my x? Negative 1. What is my r? 2. All set. So you don't cancel this with this now. That will be very wrong. I hope you know that by now. You don't cancel those, guys. You don't. So what do? You keep the 2 outside. You deal with the exponents. You cannot enter the brackets without removing the exponents. So this is the same as this bracket being written twice. Right? That's what it means. Right? And then this same thing. Oops, what am I doing? Same thing. I have negative 1 over 2 with negative 1 over 2. Right? Let's cut it here. I keep the 2 outside. Again, keep the 2 outside. What is negative by negative? It's a positive. We don't have to write it. What is root 3 by root 3? It gives us 3. All set. And then what is 2 multiplied by 2? That is a 4. Minus, what is negative 1 by negative 1? That is positive 1. What is 2 multiplied by 2? That is a 4. All set. Perfect. So do I need to cancel this? No, I don't have to, because I need to add these 4's together as like terms. So I write this 2 now as a fraction, which is 2 over 1. Then 2 times 3, how much is that? That is 6 all over 4 minus 1 over 4. And what do I get? This is the same as 6 minus 1 all over 4, basic fractions. And I'm left with 5 over 4. You can't leave our answer as an improper fraction. 4 goes into 5 once. The remainder is 1 all over 4. Beautiful. This is beautiful. These are the things that make me love maths. Like, it just so it flows, guys. It has to. Like, it flows. Once you know the concepts, you flow. If you make one mistake, do not worry. You'll only be penalized once, and then you'll get the rest of the marks. Like look at what I'm doing. Even if I do make mistakes, I don't worry in my videos, because I know one mistake will cost me 1 mark. If a question is 6 marks and I made one mistake and I continue with the proper mathematical steps, I'll still get the other marks. I'll be penalized once, and I'll get the rest of the marks. I hope you get that. So let's move on. So look at that heading there, reduction. I know it's not written in a most beautiful way, but it is reduction. So I want to show you something here. So in trig, we believe in taking bigger numbers, reducing them into smaller numbers that are small enough that they make sense, and then we work with them. So where does that start? Let's say you have a number like the sine of 30 degrees, right? When you have a number like the sine of 30 degrees, let me take out my calculator here so that you actually see what I'm talking about. When I put on my calculator the sine of 30 degrees, make sure you always close the bracket. I get how much? 1 over 2, right? Let's put that down. We know that I get 1 over 2, right? This is one thing I know. Now, what happens if I put the sine of 150 degrees? Let's take out a calculator and check again. The sine of 150 degrees. Oh, guess what? It gives me 1 over 2. Let's put that down. So we are saying this gives me 1 over 2. All set? Now, let's figure this out. What happens if I put the sine of, let's Let's make this proper. Let's make this mathematically correct. What happens if I put the sine of 210 degrees? Right? Let's take out a calculator again and see. The sine of 210 degrees. Guess what? I get a half, even though this time it's a little bit negative, but I still get a half. You see that? So let's put that down. So this gives me negative half. And then what happens if I put a sine of 330 degrees? How much do I get? Well, I bet you might have guessed it, that you are definitely going to get a half. All set? Even though this one is also a little bit negative. So let's put that down. Negative half. Now, what's happening here? Why are all these sine functions giving us halves? Some halves are positive, some halves are negative. Now, the trick is here, guys. Trick is here. Whenever you have a Cartesian plane, you know that this is your 90 degrees. Sorry, what am I doing? Making an error on a basic Cartesian plane. That shouldn't be possible. So, you know that this is your 0 degrees. This is your 90 degrees. This is your 180 degrees. This is your 270 degrees. And when you get back here, this is your 360 degrees. All set? Now, where is the 30 degrees in this Cartesian plane? You will definitely find your 30 degrees here. This thing will measure 30 degrees from here to there. 30 degrees. Right? We are saying this gives you 1/2. All set? Now, let's use another color there so that you get what I'm talking about. Now, where would you find 150 degrees? Between 90 and 180, 150 degrees will be somewhere around here, which means this thing will measure how much? 150 degrees. But, there is something here. If this is 150 degrees, what is the angle from this part to get to 180? How much do we need to move from 150 to 180? We need 30 degrees. Now, do you see that? Moving from X here to the terminal, it took us 30 degrees. And then here, from this terminal to the X value, it's 30 degrees. Is that a coincidence? Well, if something happens 2 times, it might be a coincidence. Right? Let's use this now. Where is a 210 terminal? A 210 terminal, we know it's definitely above 180, but it's less than 270. So a terminal of 210, it's somewhere in here. What are we saying? We are saying when you measure from 0 degrees all the way up until there, that thing definitely gives you how much? 210 degrees, right? But then, what happens if you move from this 210 degrees, you go back to this thing? How many units is it to move from 210 to 180? Well, I bet you would have guessed it. It is 30 degrees. You see that? Every time we move from the terminal to the x-axis, for some reason, it takes us 30 degrees. All set? Now, let's use another terminal to verify that. Look at this. 330, right? 330, it's definitely above 270, but it's less than 360, which means now it is in this terminal. All set? So, which means if ever I'm to measure from here all the way up until here, I would have measured 330 degrees. All set? But, again, measuring from this terminal to the x-axis again, moving from 330 to 360, how much do I need? You guessed it? I need 30 degrees. So now what happens? What happens here is that I do realize that the sine of 30, the sine of 150, the sine of 210, the sine of 330, they all give me half for some reason. Why? Because they are all 30 degrees away from the x-axis. Wherever we are on the Cartesian plane, whether we're in the first, second, third or fourth quadrant, they are always 30 degrees away from the x-axis. So now, how does this help us, you ask? Let me show you. So here we have these values. Let me put a Cartesian plane here because we need it. I don't know why I removed that. Let me put a Cartesian plane. 0 degrees or 360 degrees, 90 degrees, 180 degrees, 270 degrees. Let's put a cast there. Perfect. Now, what's happening there? So this, it is a simple sine of 30 degrees. All set? Now, and it gives me half. It's a simple. What I want to work with here, I need to work with acute angles. That's what I need. I need to work with acute angles. So which means I'm avoiding bigger angles like this one here, the one that we're going to. So I'm going to say here, what forms the sine of 150 degrees? So I'm reducing now. And for me, this is where the topic of reduction comes in. When I reduce, I use 180 degrees and I use 360 degrees all the time. So let's reduce this now. We are saying 150 degrees is such an unnecessary number which is too huge for me to deal with. I can reduce this number into an acute angle. So how do we do that? 150 degrees is the same as me taking 180 degrees, a major angle, and I remove simple 30 degrees there. All set? Perfect. Now, when I take 180 degrees and remove 30 degrees, in which quadrant will I land? So here is 180 degrees. If I remove 30, I'll land definitely in here. Definitely in this quadrant. Quadrant number 2. In quadrant number 2, how is the sign? My sign is positive. So I write positive sign and then I choose the angle that I just subtracted. 30 degrees. I'm saying now the sine of 150 degrees, it's the same thing as the sine of 30 degrees. So I don't need to work with a big number like this. I can just reduce it to a small number like this. Moving on to the next one. The sine of 210. What forms the sine of 210? Well, the sine of 210 is formed by me taking 180 degrees and adding a small 30 degrees there. This gives me 210. And then after that, I look at this number here. 180 plus 30 degrees. Where in which quadrant is that? Here is 180. When I add 30 degrees, I'll land somewhere in here. This is quadrant number 3. How is sine in that quadrant, or which function is positive? Only the tangent is positive in there. So which means my sine is negative. And I will take the number that I just added there, which is 30 degrees. So what I'm saying here, I'm saying instead of me using the sine of a big number like 210 for me to solve my questions, especially where they say without a calculator, I can just reduce this into the negative sine of 30 degrees. And then it will be easier for me to work with a smaller number. Make sense? Perfect. Let's move on to the last one now. So here it says the sine of 330 degrees. Again, this number is unnecessarily huge. Remember, I used the major numbers 180 and 360. I can just reduce this number by saying the sine of 360 degrees, remove 30 degrees because it's the same as 330. And what do I get there? First, you decide. In which quadrant is this? Here is 360. When I remove 30 degrees, I'll land in this quadrant, which is quadrant number 4. In quadrant number 4, which function is positive there? cosine is the only positive function in quadrant 4. So which means this sign, it must be negative in there. So I'm taking this value here that I just added. So I'm saying, instead of saying the sine of 330 degrees is such a big number, I can reduce this into an acute angle of negative sine 30, and this will give me the same answer. Make sense? Let's prove that. Let's prove that. We're just going to prove the last one. So we are saying here the sine of 330, how much do we get? Negative half. Now let's check the negative sine of 30. Negative sine of 30, how much does that give us? Negative half. You get what I'm saying? So we are avoiding to work with a bigger number. We reduce that into a smaller number so that it's easier for us to work with acute angles than these large numbers like 330. Hope it makes sense. So again, where is this needed? Let's move on and I'll show you. So here are the questions here. They're saying reduce the following angles into their acute angles, into a ratio of an acute angle. So let's quickly do that. This one right here, 130, is such an unnecessarily huge number. How can we solve that? This is the same as the sine of 180 degrees, and we are removing 50 degrees there. What does that give us? We need a Cartesian plane to decide that. We need a Cartesian plane. So here's a Cartesian plane. This is 180 degrees. This is 360 degrees. Right. 90 and 270. And here's a cast. We need that casting. So 180 degrees, here is 180. If we remove 50, we are going to land somewhere in here, right? Which function is positive in here? It's the sine, and we are working with the sines, which means we are okay. That gives us a positive sine of this number here, 50 degrees. See how easy is that? Next one. B, the cosine of 200 degrees. How do we deal with that? This is the same as the cosine of 180 degrees plus 20 degrees. That's what forms 200, right? And then we look at that. Here is 180 degrees. If we add 20, we are going to land in here. Which function is positive in the third quadrant? It's only the tangent, and this is definitely not the tangent. So which means we're going to have a negative cosine of this angle here, 20 degrees. Easy as that. Next question. They want us to reduce this into an acute angle. Let's see how can we do that. So the tangent of 320 degrees. All set? How do we deal with that? This is the same as the tangent of 360 degrees. Remove 40 degrees. Right? So here is 360 degrees. When we remove 40, we are definitely going to land in this quadrant number 4. Which function is positive there? Only the cosine. So this is definitely not the cosine. So which means this one is negative. The negative tangent of what? Of this angle here, the 40 degree angle. See how easy is that? Now let's put this into a more complex situation. Let me put a question that is more complex here. So here is this question here. They want us to simplify. Now pause the video and see if you can do it on your own, and then you'll come back here. Now what do we need here? We need a Cartesian plane first. This is 360 degrees. This is 180 degrees. This is 90. This is 270. All set. And then here's my cast right there. Now getting to this one, I have the sine of 180 degrees plus theta. Here is 180. If I add an angle, a theta or anything, as long as if I add an angle, I will land here. Is sine positive here? No, only the tangent is positive, so I have a negative sign there. A negative sign of what? Of this angle here, theta, right? And then here I have a sine of 180 degrees. I'm talking about the denominator now. I remove theta. Where will I land? In this quadrant. And which function is positive? That sign is positive. So my sign will be positive here. It's a positive sign of what? Of this angle there. You see that? And then it's easily simplifiable. This cancels this. What am I left with? -1. Easy as that. Now let's throw in another one. Here's another one. So again, pause the video and see if you can do this on your own or not. So 0 degrees there and 360 degrees there. I have 180 degrees there, I have 90 degrees there, I have 270 degrees there. And here's my cast, right? So I'm getting to this one. 180 plus theta, here is 180. If I add theta, I'll end in here. So the cos is definitely negative here. So I have negative cos of what? Of this angle, x. And then here I have 360 minus theta. 360, if I minus an angle, I'll land in there. The tangent is definitely negative in this, so I have a negative tangent of this angle here, x. All set? Hope you all good. Let's put this also in brackets so that it's more mathematically correct. And then I have the tangent of 180 minus theta. So here is 180, so not theta, sorry, x. If I remove an angle, I'll land in this quadrant, which this is not a tangent. So this is a sine, and then here I have a tangent. So which means now this tangent is going to be negative tangent here. Negative tangent of what? Of this angle here, x. Right there. So it means here my negative tangent x will cancel my negative tangent x, and I'll be left with the negative cosine. My answer is a negative cosine of x. Beautiful, guys, beautiful. It's as easy as that. I hope you're good. Let's move on to the next thing now. The next part, we have something that we call a negative angle. A negative angle, it's so easy in a beautiful way. So we have 0 degrees there, we have 90 degrees, we have 180 degrees. You see how much we need a Cartesian plane? We need a Cartesian plane a lot. So this is 360 degrees, right? So what happens with a negative angle? When you move this way, anti-clockwise, you are giving us positive angles, right? But then when you move this way, clockwise, you are giving us negative angles. Easy as that. Easy as that, right? So now, what happens there? If ever I ask you for something like, let me put that back, put that. If ever I ask you for something like this, a theta, like a sine of theta, it's just going to give you a straight answer. But then, let's put a cast there. If I ask you for a sine of negative theta, now you have to consider there, when I move from here and then I go in the opposite direction to form a theta, in which quadrant am I going into? I'm going into quadrant number 4. Now, which function is positive in quadrant number 4? It's the cosine. So which means this, when I simplify it, because it's hard to deal with negative angles, I can simply say this, it's a negative sign because sine is negative in this quadrant, and it's a negative sign of what? Of this angle, the theta. Hope it makes sense. All set? It's as simple as that. So now let's put in some questions there. Let's get straight to solving some questions. So here's a question right there. I hope I copied the question correctly, because in questions like this one, just like people in exams, the most mistake that people do is that they copy the question in a wrong way, and then they lose a mark there. What is the first step? I bet you would have guessed it. Cartesian plane. This is 0 degrees, this is 90 degrees, 180 degrees, 270 degrees, and this is also 360 degrees. Cast. You always need a cast there. Then we go into solving the question. The sine of a negative angle. Negative angle, remember, we are just moving into this quadrant. Sine is negative in this quadrant, so I'm going to have a negative sine of what? Of this angle. A negative sine of theta multiplied by, I have a tangent of 180 plus theta. So here's 180. When I add an angle, I'll land here. Tangent is positive in here, so I will have a positive tangent of what? This angle that was just added. This way. All set? Multiplied by the cosine of 180 minus theta. So 180, if I remove a theta or I remove an angle, I'll land in here. The only thing positive here is the sine, so which means this cosine is going to be negative. So it's negative cosine of what? This angle. Like that. Remember, we used the major angles, the 180 and the 360 only. Never use the 90, never use the 270. I'll tell you when to use them. So this, we go to the denominator, 180 minus theta. When we remove theta from 180, we land here. This is the quadrant. Let me label this quadrant. Let me label them so that you see them. Makes things easier. Let's use a red pen. So this is theta. This quadrant, it's called negative theta, or it's also called 360 degrees minus theta. This quadrant, it's called 180 degrees minus theta. This quadrant, it's called 180 degrees plus theta. So now I'll use this as a reference. I know this is in this quadrant. This is in this quadrant. This is here. And here I have two things. The 360 minus theta, or I have this part here, the negative theta. See how beautiful is that? Now, this 180 minus theta, it's here. Is the sign positive here? Yes, the sign is positive. Oh, this is beautiful. It even works faster. The sign is beautiful here, so I have the sine of theta right there. Tangent of 360 minus that, 360 minus theta, it's here. Tangent, it's negative in here, so I have a negative tangent of theta. Oh, this is fast. Cosine of theta, cosine of negative theta. This is the quadrant of negative theta, and the cosine is positive here. So I have cosine of theta. Just have a positive cosine of theta there. Then we work forward there. I'll deal with the signs later. Now I need to deal with the functions. Right? So a cosine will remove a cosine. I'm not working with the signs, I'm only working with the functions. A tangent of theta will remove a tangent of theta. A sine of theta will remove a sine of theta. Beautiful. And then what do I have to deal with? Negative times negative, that is positive 1. Here I only have this negative, so it is negative 1. So my final answer, it's just 1. You see how beautiful is that? How everything just unfolds, and you even discover new things, like this thing I just thought about right now here. It's so beautiful. It just makes things easier. It shows that the more you do, the more these things become natural to you, the more they happen like second nature. Revolution. A revolution in trigonometry, it's beautiful, very beautiful. We're not talking about the history revolution here, things like the French Revolution and things like that. No. This is maths. When we talk about a revolution, we are talking about the revolution, like counting, like measuring an angle. It moves 90, 180, 270, gets to 360 again. That's a revolution, right? Revolution. That's the revolution we're talking about. When measuring an angle gives you a full circle, it revolves. All set? So now, so here is something beautiful about the revolution. The beautiful thing is that whenever you have the sine of theta plus 360 degrees, it just gives you, like, it lands there. And you'll see what I'm talking about. Look at this. So I start with the revolution. If I move 360 degrees, boom, and after that I move theta, poof, up until here. It's the same thing. It's like I moved without having the revolution this way. You see that? So when I make a revolution and move a theta, it doesn't show that I made the revolution. The revolution is just there and I have my theta, right? So same thing applies here. Let's say you have, so I'm saying theta plus its revolution. So the sine of theta plus its revolution is just the same as the sine of theta. It doesn't show that I've added the 360 degrees there. That's what I'm saying, right? It's just this, right? We are still reducing things that are not necessary. We are reducing them. All set. So let's say again we have the cosine of theta plus 720 degrees, right? What is 720 degrees? This is the same as 360 degrees plus 360 degrees, right? So which means I'm like making the first revolution, boom, then the second revolution, boom, and then I move theta. I end up there. But then again, where I move 2 revolutions or what, I still land here and nothing changes. So which means this is the same as the cosine of theta, right? These 2 revolutions that happened are not necessary. All set. Last one to make you understand. Let's say you have the tangent of theta plus 1080. Now, what forms 1080? It's when you have 720 degrees and then you add 360 degrees there, right? This is already 2 revolutions. Now we're adding the 3rd revolution. So it's like me saying 1, 2, 3, and we move theta right there. All set. All these 3 revolutions that happened are not necessary there. We can just cancel everything out and be left with the tangent of theta. Hope that makes sense. So this is us reducing. Now let's get to the part of reducing now. Let's get to that part. So here we have to simplify the following. This is way too different from the story of having 180 degrees minus theta. It's a little bit different. So we need to work around it. So let's do that. How would I solve for the first question? A. In this case, I see that I have a negative 180 degrees. So I'll keep on adding revolutions to this thing until it gets fixed. I hope that's it. So here I have the tangent of theta minus 180 degrees. So I'll add a revolution there. How much is a revolution? 360 degrees, right? I'll end up with what? With theta. What is negative 180 plus positive 360? It's positive 180. Right, so now this is where I want it to be. So now I fix this. I put the 180 first. So here's the 180 degrees plus theta. Now when I have something like this, I have the standard form that I've always been working with. Standard form, it says this quadrant it's theta. This one is 180 degrees minus theta. This one is 180 degrees plus theta. And this one it's 360 degrees minus theta, or we also call it negative theta. All set. So, and then we have our cast methods, our cast system. Put a cast there. C-A-S-T, cast. See how beautiful is that? Now we get to the working part now. Where is this quadrant? This quadrant, it's here. Is tangent positive there? Yes. So I have the tangent of theta. So instead of me having something as complex as this, I can just say that I have the positive tangent of theta. It's reduced now to something that makes more sense, that is way easier to deal with. So next, here, let's say we have the tangent of negative theta plus 720. Now this is beautiful. This is very beautiful. Now we have the 720 there. All right. So whenever, all the time. Oh, this is not a plus. This is a minus from the question. Here's a question B there. Let me remove these things. It's so unnecessary. This is a minus 20. Minus 720. There we go. So now, what happens there? I have a negative 720. They've already removed a revolution from that diagram. So because I have a negative revolution, I'm going to put there a positive revolution. But do I need one revolution? No, I need two revolutions because they also remove two revolutions. So I'm going to say plus 720 degrees. You see that? So the negative two revolutions cancel out with the positive two revolutions. So I'm left with the tangent of negative theta, right? Which quadrant is negative theta? It's this one, the fourth one. So now I'm saying that tangent is negative in the fourth quadrant, and then I put the angle there. Beautiful. So now, so far the things that we spoke about on this video, we are bringing them here now. Like we are busy introducing concepts bit by bit, one at a time, and as the questions move forward, we bring all the concepts together into one question. All set? So now here, Cartesian plane. Cartesian plane is the way to go, guys. So you have a Cartesian plane, you'll never go wrong. All the time. You have a Cartesian plane, you won't go wrong. You need this. So this is theta. This is negative theta. This is also 360 degrees minus theta. This is 180 degrees minus theta. And this quadrant is 180 degrees plus theta. All set. And then we have our cast system there. Works perfectly all the time. So now, negative theta of a tangent, what is that? This is a negative tangent. Sorry, this is not theta, this is alpha. We're working with alpha. Right, so everything is alpha there. I hope you can see it. It's all alpha there. Now, that is the negative tangent of alpha multiplied by 1080 degrees minus alpha. So what happens there? The problem is this is a revolution. How many revolutions? They took 720 and they added 360 degrees. That's how they got to 820. So this is two revolutions and this is one revolution. So they've added three revolutions to this concept. How do we do that now? The best thing to do is to subtract three revolutions. So the cosine of 1080 degrees minus 1080 degrees minus alpha. There, beautiful. And then we look at this one. This one is not about the revolutions. This is about the quadrant, right? This part here. Quadrant of 180 plus alpha. Here is the quadrant that is 180 plus alpha. Which one is it? It's where the tangent is positive. So I have the tangent of alpha. And then cosine of alpha minus this. What happened here? This needs to be fixed. So now, for me to fix this one, I have to add a revolution right there. I have to add a revolution. So I have the cosine of alpha minus 180 degrees. Even though they didn't move a revolution, I'm going to add a revolution, 360 degrees. Just one revolution. Just one. It's enough. So now this revolution gets removed by this revolution, right? and this gets removed by something there, right? Let's start here. So here I have a negative tan alpha with a tan alpha. This cancels that. I'm left with negative, and this is the cosine. Hope that's visible. So what is left there? It's the negative alpha in there, negative alpha. The two revolutions cancelled each other. Hope you see that. Perfect. And then here, what is left? I don't have a negative here. I just have a cosine. Cosine of what? Let's put this. Cosine of alpha. What is negative 180 plus 360? That is positive 180 degrees. Beautiful. So, afterwards, we deal with this issue here. A negative alpha is in the fourth quadrant. So is a negative alpha positive or negative? It's positive, so which means this won't be affected. I have a negative cosine there because the cosine is negative, and then I have an alpha there. The alpha doesn't change anything. Why? Because the quadrant it's in, that's where the cosine is positive. And then here I have this. This, if I rewrite it properly, is the same as the cosine of 180 degrees plus alpha. I'm sure you all can see that. So where is 180 degrees plus alpha? Here's 180 degrees plus alpha. Which one is positive? That's the tangent. So which means the cosine here is negative. And what do I get afterwards? Just 1. Perfect. So after all this, let me see how much am I left with. How much have I done? Right, so we did the general that we've been doing cast, we've been doing revolution, we've been reduction, we've been doing revolution, and we have to do the others. See how beautiful is that? Math is beautiful, guys. So let's get to the others. The others won't take us a lot of time. So these things that you see here, they're actually going to just add up. You'll see them as they do. Co-functions. So for co-functions, what I need you to remember here, it is complementary angles. Right there, the word complementary angles. What are complementary angles? Complementary angles, those are angles that add up to 90 degrees. I hope you still remember them. So now here, talking about those angles, let's say we have the following. Right, whenever we have the sine of 30 degrees, we said that gives us how much? That gives us half. Whenever we have the cosine of 60 degrees, that gives us how much? Half. Right. So what is happening here? Let's choose something else. Whenever we have the sine of 30 degrees, we get the root of 3 all over 2. Whenever we have the cosine of 60 degrees, we get the root of 3, you would have guessed it, over 2. Beautiful. Now, what's happening here? I'm saying to you now, whenever I have the sine of 30 degrees, this should be the same as what? As an opposite function, which is the cosine. But it's supposed to be the cosine of what? Not the cosine of 30 degrees. No. It's supposed to be the cosine of the complement of 30. So the complement of 30 is any number that I can add to get to 30 degrees. Is that fine? I mean, to get to 90 degrees. Sorry, right? So this, how much do I need to add to get to 90? 60 degrees. That's how we know that. All set? Let's say now that you have the sine of 70 degrees. What is the complement of the sine of 70 degrees? Well, the complement for sine is a cosine, right? And then the complement of 70, how much does 70 need to get to 90? That is 20 degrees. All set. So we have complements. We have an angle and a complement. Let's take another one. Let's say you have the sine of 50 degrees. Why do we keep on doing sines? Let's do the cosine now. Let's say you have the cosine of 50 degrees. Now, if you have the cosine of 50 degrees, what is the complement of that? Well, the complement of a cos is a sine. The complement of 50 degrees, for 50 degrees to get to 90 degrees, we add how much? 40 degrees. So we are saying the cosine of 50 is the same as the sine of 40. Beautiful. Beautiful. So now let's come with the rule there. What happens? What happens is that I know that whenever I have the sine of theta, what's going to happen? The complement of sine will be a cosine, and the complement of theta is any number that I need to move from theta to 90 degrees. So I'm going to say 90 minus theta. You see that? So if I have a sine, its complement is going to be this one. If I have a cosine of theta, its complement is going to be the sine of an angle that I can add onto theta to get to 90. So it's 90 degrees minus theta. So this and this are the same. So here are some activities here regarding cofunctions and everything we've done so far. So let's get straight to it. So here we have sine. How am I forgetting? We need a diagram, guys. 0 degrees and 360 degrees. I have 90 degrees here. I have 180 degrees. I have 270 degrees. This is my cast. This is theta. This is 180 degrees minus theta. This is 180 degrees plus theta. This is negative theta. This is 360 degrees minus theta. Beautiful. This way. Let me put in some red borders around it. Like, it's so beautiful to have it this way. It makes everything looks easier. And I don't even struggle. Like, it's so beautiful. Perfect. So now, to get to solving this part, the sine of 90 minus theta, what are we supposed to do there? We are supposed to see 90 minus theta as a cofunction. Now, remember the thing about cofunctions, they happen between 90 degrees and 270 degrees. There's no cofunction here, there's no cofunction here. All set. So now, whenever I have, what is the cosine? The cofunction of a sine, it's a cosine. All set. Beautiful. Now, it's the cosine of what? It's the cosine of this theta here that we were just subtracting. So we put a theta there. Remember we said sine, it's cofunction, it's the cosine, and then this angle now, the 90 degrees minus theta, it's the difference between theta and 90. So the amount needed to move from theta to 90, that is what it is here. So now here, what we have is that here we have theta right there, multiplied by the sine of theta. Is there anything we can do there? No, it stays as the sine of theta. It's beautiful this way. And then here we have the cosine of theta. So the cosine of theta stays the way it is on the denominator part. And then afterwards we have this now. What happens then? We have the cosine of this value here. But then how do we deal with this one? See, the thing with this one, with the cosine of theta, 90 minus theta is in the first quadrant and everything is positive there. That's why this one stayed positive. This one is 90 degrees plus theta, which is definitely not in the first quadrant. This is in the second quadrant. So since it's in the second quadrant, it means our cosine was negative in there. So we attach a negative there, right? And then the inverse of a cosine, it's what? It's a sine. So we put sine there. It's the sine of what? Of this angle there, the angle in question, theta, this way. See how beautiful is that? Then this cancels this removes that. What am I left with? I'm left with -1. Beautiful. So second question B, I have this thing here. Can this be a cofunction? No, it's not operating on the section of 90 degrees and 270 degrees, so we don't work with cofunctions there. So what are we working with there? We are working with reduction. How do we reduce this? We are already using the major angle 180 degrees. All set. Which quadrant is 180 minus theta? Here. Is cosine positive there? No. So I have a negative cos. All set. And then it's a negative cos of what? Of this angle here. So I have an x there. All set. So let me put this in brackets because I have a lot of things and I don't want to create a mess there. And then can this have a cofunction? Yes. Why? It's operating on a 90-degree angle. For as long as a function operates on the 90 and 270-degree angle, we are working with cofunctions. And whenever we are working on the 180-degree and the 360-degree, we are working with the reduction. All set. We are bringing everything together now. We are combining everything. So now, cosine of 90 degrees minus theta, where is this? This is in the first quadrant. So everything is positive there. So what is the cofunction of a cosine? It's a sine. It's a sine of what? Of this angle in question here. Sine of x. See that? So next, multiplied by the tangent of negative theta. Where is negative theta? The fourth quadrant. Is the tangent positive there? No, the tangent is negative there. So it's the negative tangent of x. See that? Beautiful, beautiful. And then now we have this one, the sine of 180 degrees plus x. Is this a cofunction or a reduction procedure that we need to do? We are reducing here because we are on the 180-degree level. So now, where is this quadrant? This is the third quadrant, and sine is definitely not positive there. So I have negative sine of what? Of this angle in question, the negative sine of x. All set. And then this one there, I'm working with a 90-degree angle. Is it reduction or is it cofunctions? It's a cofunction that I'm working with. So now 90 plus theta, what is that? That is the second quadrant. 90 plus theta is sine positive there. Yes, sine is positive there. So which means whatever I'm using there, it will remain positive. Now, what is the cofunction of sine? It's a cosine. The cosine of what? Of the angle in question there, which is x. We all see that? Perfect. So the cosine of x will cancel with the cosine of x. The sine of x will cancel with the sine of x. You see that? Negative and negative will give me a positive. And then I'm left with negative tan x, which is negative 10x. All set? So which means negative times positive, that gives me a negative. So negative tan x is my answer there. As beautiful as that. Like everything just adds up. The more you do, the more it becomes natural to you guys. Let's move on to the next one. So I want to show you this question here. These ones are one of the interesting questions. Let's put A there. So here we have the sine of theta minus 90 degrees. So this is not in the standard form that we want. What's supposed to happen there? we are having a negative 90 degrees there, which is usually not how we deal with things. So what are we supposed to do? You're going to say the sine of theta minus 90 degrees, and then here you add 1 revolution. See how beautiful is that? Then you'll end up getting what? The sine of theta negative 90 plus 360, that's positive 270. This is the same as what? This is the same as sine 90 with a positive 270 plus theta. Now here it's beautiful because of this. Now we are dealing with the cofunction, especially when it's 270. So now you have this cast, right? 270, it's here. Once you add theta, you are landing here, right? Is the sign positive in here? No. So which means you're going to have a negative answer. What is the cofunction of a sine? It's a cosine. The cosine of what? Of this angle in question here. See that? Beautiful. Let us do another one. Let me quickly erase this. Let us do another one. So let's say we have B, the cosine of theta minus 90 degrees. Same thing. Please try to pause the video and see if you can win. So what happens here is that obviously you need a Cartesian plane. So you're going to say this has a negative 90 degree. This is not in the standard form that we want. So we're going to say the cosine of theta minus 90 degrees. We add 1 revolution there. After we add a revolution, we are left with what? Negative 90 plus 360, that's 270 degrees, right? And then when it's 270 degrees, now we can organize this. 270 degrees plus theta. It's now organized in terms of a cofunction. Now 270, let me write my cast there. Now 270 plus theta is where? It's on the 4th quadrant. Is the cosine positive in the 4th quadrant? Yes. So which means my answer will be positive. What is the cofunction of cosine? That is the sine. The sine of what? Of the angle in question. This way. Beautiful, guys. Beautiful. So far we dealt with what? We dealt with cofunctions. Beautiful. We did this, we did this, we did this, we did this, and we did this. Cofunctions. Now we are going to reduction involving numerical angles. Beautiful. You'll see it. So in Trig, guys, we are trying to get you to do this topic as much as possible by avoiding the calculator. Like, we keep on throwing a lot of things, the reduction and the cofunctions and all those things, just to make you avoid the calculator. So, special angles, the reduction involving numerical angles. Now we are reducing, but how are we reducing? With numerical angles. Now, here's what happens. You need to know the values of all the special angles. How? First, it starts by you knowing the special angles exactly in their order. We have 0 degrees as a special angle. We have 30 degrees as a special angle. We have 45 degrees as a special angle. We have 60 degrees as a special angle. And we have 90 degrees as a special angle. So, with those special angles, you need to know how to create special triangles. Now, let me see if I can create that with a proper instrument. No, it will take my time. Let me just use what I know. So, you are going to first create what looks like a Cartesian plane. This is supposed to be vertical. So, please don't judge me harshly. This is also supposed to be horizontal. So, please don't judge me harshly. Afterwards, you draw 3 lines. Make sure you space them out evenly. So, 1. Oops, this is terrible for me. This is also terrible. Let me remove it. 1, 2, 3. Perfect. Perfect. So these things here, they must form more or less like triangles. So with this case, what happens? I want you to cram it exactly this way. So here you have 0, the root of 0. Here you have root of 1. Here you have root of 2. Here you have root of 3. Here you have root of 4. And right there, exactly right there, you have another pair of a coordinate. Root of 0, root of 1, root of 2, root of 3, root of 4. All set? And then all the time, your r, it's always 2. Your r, it's this terminal, it's this terminal, it's this terminal, it's this terminal, it's this terminal. All these terminals that you see, these are your r's, right? So this terminal here that you see here, this is a 90-degree terminal, right? And then this is a 60-degree terminal. And this is a 45-degree terminal. And this is a 30-degree terminal. And this is a 0-degree terminal. Now, what you see here, you're looking at coordinates. This is a coordinate. How so? You have x and y. This is also a coordinate. You have x and y. This is also a coordinate, of course. You have x and y. This is a coordinate also. You have x and y, and I bet you guessed it, this is also x and y as coordinates. Guys, I don't know how to emphasize this perfectly to you, but you are going to need this diagram big time. You are going to need this diagram, guys. Make sure you cram this diagram the way I've created it for you. You'll need it. You'll 100% need it in a test. You will need it, and you'll need to know how to create it. So these are the special angles. Now, when I'm looking for the sine of 30 degrees, just know you have to refer to this. This is your r, and you have your x and y's. What is the sine of 30? You're comparing x over r. Right, your r is how much? It's 2. What is the x in sine 30? You look at the terminal of 30, terminal of 0, terminal of 30. Right here, your x value is 3. No, root 3, sorry. Almost made a mistake there. This is root 3. You see that? Root 3 over 2. So please make sure, guys. Make sure you don't do any mistakes. You need this terminal. You definitely need this diagram. You need to cram out. You need to cram how to create it. So now, let's get to the meat and bones of this thing. So here are the following questions, saying calculate the value of the following expressions without the use of a calculator. Right. So starting with the first one, the sine of 240 degrees. So there are several things that are here. We have I'm not sure about cofunctions. They might be there, but we definitely have reduction, right? So look at this one here. Look at this one here. This number, it's too big for us to work with it. How can we reduce this into a smaller number? Right? So this is going to be the sine of 180 degrees plus 60 degrees. All set. This is equals to, right? It's equals to what? We are reducing this now. We are reducing this. For us to reduce this, what do we need? We need a Cartesian plane. This is theta. This is 180 degrees minus theta. This is 180 degrees plus theta. This is 360 degrees minus theta, or it's just minus theta. And then we write our cast there. Cast. Perfect. Now, What is 180 plus 60? 180 plus 60, it's here, and the sign is negative. So I have negative sine of 60 degrees, and I have to solve for that. And then how do I solve for this without a calculator? I go back to this, my special triangle. Let me create it properly here, so that now I can keep on using it easily. So I have, let me see this with the design. So here's a diagram right there, and then we write everything as it's supposed to be. This is the 90-degree terminal, this is the 60-degree terminal, 45-degree terminal, 30-degree terminal, 0-degree terminal, and then we write our coordinates as x and y coordinate. So we start with 0 here, square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. You see how I'm teaching you to work with special triangles right here. When they say without a calculator, this is what you do. And then here the y values: square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. Remember, our coordinates are in the form of x and y. The first coordinate is the x, the second coordinate is the y. And then how much is our r for all the terminals? Our r here, as we said, is equals to 2 all the time. So now we are going to borrow this to answer the questions that we had there. What is the sine of 60? It's supposed to be negative and then a bracket. Opposite over hypotenuse. What is the hypotenuse? The hypotenuse, we said it's 2. What is the opposite at 60 degrees? Here is 60 degrees. Our y value is root 3. So we go there, and then we have root 3. All set. And then you get your answer there. Root 3 over 2. Now, moving on to the next one. Let's remove this. Moving on to the next question. Here it is. The cosine of 330. So, the cosine of 330, do you see where is that? This is the same as the cosine of 360 degrees minus 30 degrees. Is this a cofunction or a reduction process? You guessed it. Definitely reduction. And then, so here, the tangent of 135, this is the same as, how do we deal with 135? 135 is such a huge number, so I have to say 180 degrees minus 45 degrees, this way. You see that? So I'm working with reduction here. Now, cosine in this quadrant, 360 minus theta is positive, so I have the cosine of 30 degrees all over. This is the second quadrant, 180 minus theta, and the tangent is negative there, so I have negative 10 of 45 degrees. All set? Perfect. So this now, the cosine of 30, I know that its radius or hypotenuse, it's 2. And then what is the adjacent for this hypotenuse? What is the adjacent for 30 degrees? Let me go there. 30 degrees adjacent, it's root 3. So here I have root 3. And then here I have divided by. You see this division line? It means I must divide them. So divided by negative, here's a negative, and then a bracket. For 45, my opposite for 45 is root 2, my adjacent is root 2. So I have root 2 over root 2. Basically this cancels and then we are left with 1, right? So I have root 3 over 2 divided by negative 1, which is the same as negative root 3 over 2. Easy as that. This is beautiful. The last one, C. Right. What happens there? We know that we have a square, right? So basically this is us having, in brackets, the sine of what is 315. This is 360 degrees minus 45 degrees. We are reducing this, right, from this complex number into a smaller number. Probably will give us a special triangle, and we'll work with that. And then the squared was the sine was a square, so we do that. Then minus 1 all over. Here I have the sine of what is 210. This is 180 degrees plus 30 degrees, and this whole function is also squared, right? Perfect. So now we have this part here. I end up having the sine, and then which quadrant is this? This is the fourth quadrant. How is the sine there? The sine is negative, so I have negative sine of the angle in question, which is 45 degrees, right? And then we square that. It's equals to 1. All set. All over. What do I have here? Sine in this quadrant, which is the third quadrant. How is sine in the third quadrant? It's negative, right? For which angle? For this angle in question here, 30 degrees. And this is also squared, right? So we can remove this now. I think we are done with it. So now in this case, whenever we have this is the same as us having negative sine of 45 degrees multiplied by a negative sine of 45 degrees. And then we have a minus 1 all over. I have negative sine of 30 degrees all over the negative sine of 30 degrees, because it's also squared, right? And then here, what do we end up having? Basically, this is difference of two squares. I'm not sure if you can see that, but this is difference of two squares. Because of this, it's one term, and this is one term. So I open two brackets there. I can factorize that. I'm not sure if you all can see that. So I have this sine. The negative and negative will cancel out, which will make this whole thing positive. So let's remove the negatives. Boom, boom. Because when you multiply two negatives, you get a positive. Same thing applies here. This negative and this negative, they disappear. Now, what happens? I have the sine 45 minus 1, because of this is difference of two squares, right? And I have the sine 45 plus 1, right? And then here we have the sine of 30 degrees all over the sine of 30 degrees. All set? Now, how do we move forward here? Let me quickly erase that. This, we look for that. We are going to say the sine of 45. We go to this. The sine of 45, it's y, which is root 2 over 2. So we go there. This is the root of 2 over the hypotenuse minus 1. And then same thing, sine of 45, it's the root of 2 over the hypotenuse, which is 2 plus 1. And then the sine of 30, here it is. I have opposite, which is the square root of 1, it's 1, all over the hypotenuse, which is 2. So here I have 1 over 2 multiplied by 1 over 2. All set. So when I multiply this I must end up getting 2 over 4 minus 1 all over 1 over 4. Right? Please calculate that and verify with me, but I bet this is how much you're supposed to get as far as I'm looking at it. So what is the next thing then? What is the next thing? I'm supposed to add these numerators, basic fractions type of questions. So I have, this is half, this is 1 over 2. So if I have half minus 1, I get negative half divided by, because here's a division line there, divided by what? By 1 over 4. Right? So I have 1 over 2 multiplied by 4. Because I'll send this 4 upwards, right? So which means I'll have negative 4 over 2, which gives me negative 2. As easy as that. Beautiful. Beautiful. I love solving questions like this, whereby I have to do a lot of thinking, a lot of planning before I get straight to the answer. So now what do we have? So far we did the reduction. Let's choose a red one. Almost done, guys. Reduction involving numerical angles, and then we did that with the special angles, whereby you need to learn those special triangles and how to create them. Avoid using the calculator, guys. It's so unnecessary, and most of the times it will get you wrong answers, because I bet you don't know how to use the calculator. Okay. Now let's move to non-special numerical angles. Sorry for that. So here we go. Oh, not the red one. So here's the following. It says simplify without a calculator, of course. So this is where, if they say without a calculator, it means you have to use the diagrams and also the special triangles. So how do we do that? Let's get to this one. The sine of 110, what do we have there? The sine of 110 is going to lend us where? We're going to have something like the sine of 180 degrees plus 70. No, minus 70 degrees. Right there. And then what happens with this one? Here we have plus, this is the same as the cosine of 180 degrees plus 20 degrees for us to get to 200. Plus we have the sine of 360 degrees minus 45 degrees for us to land there at 15. All right. And then where are we going here? This is in this quadrant. Let me go check from the previous page. Oh, it's not there. Okay, let's create a Cartesian plane. So here's a Cartesian plane. Theta, negative theta, 360 degrees minus theta, 180 degrees plus theta, 180 degrees minus theta. And then we have our cast. So here's cast. Perfect. Then let's get back to the business of this question. So this is in which quadrant? The second one, and sine is already positive there, so I'm going to have the sine of 70 degrees plus, and then here the cosine of 180 plus that, which quadrant is that? The third one. And how is cosine there? It's negative. The negative cosine of 20 degrees plus, this is what? The fourth quadrant. How is sine there? Sine is negative, so I have negative sine of 45 degrees, and this is a special angle. It's a special angle, so hopefully it will make things easier. And now what do I have here? This now looks not solvable, but if you look at it properly, you will realize that here you do not only have a reduction as we applied in the previous step, but you also have a cofunction. Sine 70. What is the cofunction of sine 70? All right. The cofunction of sine 70 is a cosine. Right. It's a cosine of how much? Of 20 degrees. Because this is the difference. This is the... What is that? What is that? What is that? What is that? The complement. Yes, that's the word I wanted. Because of 20 degrees is the complement of 70 degrees. All set? Yes. And then here you have positive times negative. Here you have negative. And then you have the cosine of 20 degrees. Oh, look how that easily works out. It's so beautiful. I never thought it would happen. So here, positive and negative. I have a negative, and then you're looking for the sine of 45 degrees. How do you find the sine of 45 degrees? Special triangles. So you go to special triangles. You already know that your r, it's always 2. So here on r you place 2, and then you're looking for the y value in 45 degrees. Let's go there. 45 degrees, your y value is how much? Root 2. So then we come back here, we put root 2 here. We put root 2 in brackets. Right? We continue solving for this one and this one. They cancel out because they are values of the same magnitude with opposite signs. And then here we have negative root 2 over 2. And it's already rationalized. So it's perfect. See how beautiful is that? This is so nice. So there is a way of you dealing with non-special numerical angles. There is a way. Not non-special numerical angles. What happens if you have a number that is not a special angle and it's found in your functions? The thing is that those numbers will eventually have to cancel out until you are left with the special angles, and then you substitute out the special angles from your special triangles, the ones that you know by heart by now. All set. So now let's move on to the next concept now, which is identities. So let's see how far we are. Identities. So we did this. Now we are here on identities. Tricky. So when we talk about identities, I wish I can find a more beautiful way to explain to you what are identities. But here's what we are going to do. For grade 11, there are some things that we refer to as the basic identities, which means consider this as the rules in trig, that these things are this way. So firstly, let's say you have the sine, the square sine of theta plus the square cosine of theta. Whenever you have this, this is equivalent to 1. That is the first identity you should know. The second identity, it's the one of the tangent. It says now, whenever you have the tangent of theta, that tangent, it is the same as us having the sine of theta all over the cosine of theta. That's how it is. So please cram these things this way. These two identities, these are the main things that you need from here onwards to answer the questions that follow. Bear in mind that you have to substitute these things. Now let's go back and configure what we've done so far. We've done general trig. What else we've done? We've done reduction. And then we've done reduction with special angles. We've done reductions without special angles. And we've done cofunctions. So far, be able to keep those things in your mind and then put them into practice whenever you see the opportunity, all the time. So let's see what we can do with that, with this, the identities. So here are the following two questions about trig identities. So you know what people hate about trig identities? The Trig identities is the type of math whereby the examiner will give you the question and they will give you the answer. All we want is for you to give us what's in between. This is what maths is about. Maths is not about the answer. It's about the steps in between that get you to the answer. And the examiner will do that to you. They'll definitely do that. So here you have a question and then you have the answer. And then they're asking you, show us the step in between. Show us the steps in between that what's on the left side is equal to the right side. So let's do that now. Let's see how we do. The first question 1. Math is beautiful, guys. It's forever beautiful. So look at this one. The first thing you have to do there is to pick a side. When you pick a side, you must always choose the most complex side. Solve that one, make it as simple as the other side, and then you will have your answer. See that? That's what math is about again. Choosing the difficult sides. So here you are going to say my left hand side is equals to, and then you solve for the left hand side. Why? Because in this case, the left hand side, it is the most difficult case. I hope you get it. So we have the cosine of theta multiplied by, do you see the tangent? A tangent of theta is a trig identity. So we can easily swap the tangent with a trig identity, which is the sine of theta all over the cosine of theta. You see, where is it useful? Right there, when we are simplifying trig equations. Who knew? We have trig expressions and we have trig equations. So plus the sine of theta. Oh, there is no other side. You just set the left hand side. So don't put the equals to 2 sine theta thing, because of you said here that you're dealing with the left hand side, and then so you put it this way as an equation or an expression. So afterwards, what happens here? This cosine of theta is a numerator, by the way, of course, right? So the cosine will cancel this cosine. So this thing now, it no longer has a denominator. Oops, I made a mistake there. So I was saying now that this fraction now no longer has a denominator because it's cosine cancelled with the numerator cosine. So what are we left with there? We are left with the sine of theta, which is this part, plus the sine of theta, which is this part. And what is that equals to? This is equals to 2 sine of theta. And then do you see this? This part here, it's exactly what we were looking for from the question. Then you make a conclusion. Therefore, the left hand side is equals to the right hand side. Never forget to make a conclusion. I hope that sank. Let's get to another one now. It's a little bit tricky, this one. So here we have this one, sine x times cos x times tan x plus the square cosine of x is equals to 1. Right. So obviously we have to choose the complex side. So let's do that. Let's use a red color here. So the left hand side is equals to the sine of x. By the way, this is where you are solving for it now, right? And do you see this tangent of x? That's an identity. So you're going to say multiplied by, what is the identity of tan x? It is the sine of x over the cosine of x plus the square cosine of x. Oops, I keep on falling for this thing of writing the right part. This way. All set. Then we move forward. We do realize that a cosine of x will cancel with this cosine of x, so we no longer have a denominator there. I'm left with the sine of x multiplied by the sine of x plus the square cosine of x, right? So which means now I have the square sine of x, because I'm multiplying a sine x with a sine x, plus the square cosine of x, right? And we know that this is equals to 1 because it's this trig identity there. So we make a conclusion. Therefore, the left hand side is equals to the right hand side. Easy as that. Beautiful. So far what did we do? We were just now working with trig identities. Boom. And then we used trig identities with reduction, those proofs there. We are left with one item on this list. Trigonometric values represented by letters. Okay. This is the last one, guys. So let's get it. This video is over 2 hours long now. I was hoping that it never gets there, but it did. And I thank you for your patience for watching up until here. It's for your own good, I promise you. So here it says trig values represented by letters. Let's do that. Trig values represented by letters. So here's what's happening here. Let's say you have an example that says if the tangent, should I say the tangent? No. If tan 22 degrees is equals to k, write down the following in terms of k. So the first one here, we have a. What is a? We have the tangent. I almost said the tangent of inwards. We have the tangent of 158 degrees. B. What do we have? We have the tangent of negative 22. C should be something a little bit tricky. So let's say the sine of 22. So see, it's going to take us a bit of time, I think. So here, in terms of k, how do we do that? First of all, whenever you see a big number like this, just know that in trig, you don't need to use big numbers. So we must use the reduction method. So I'm going to say the tangent of 180 degrees minus how much? 22 degrees, right? We are on A now. So what is this? We use the cast. This is the second quadrant and the tangent is not positive there. So I have a negative tangent of the angle in question. Which one is that? This angle in question. 22 degrees. Right? And then now we already said that the tangent of 22 degrees is k. So it means this is equals to negative k because this it's k. Also, you see how beautiful is that? Straight to the point. So here's the second one. Let me put this in brackets so that it looks more mathematically correct. So here, I'm sure this is easy for you. Which quadrant has negative theta here? It's quadrant 4. How is tangent in quadrant 4? It's negative for the angle in question, which is this one, right? Easy. And then we move on. We said tangent 22, it's k. So here I also have negative k. So this one is also gone. We're almost done, guys. Do you see that? Almost done. So here's what we know. What do we know? We know that the sine of 22 degrees compares what? It compares y over r. Right? Perfect. But then we already know what? That the tangent is equals to 22 degrees. The tangent of 22 degrees in this question is equals to k. What is k as a fraction? It's k over 1. So what is this one? This one is the y, and what is this k? This k, it's the x. See that? Perfect. So now, because we are looking for the sine of 22 in terms of k now, we have to look for whatever we need. In this case, we need r, right? So let's find r. How do we find r? We know that r squared is equals to x squared plus y squared, according to a triangle, according to a right angle triangle. We are looking for a r. We already have an x, which is k, and then we already have a y, which is 1. All set? Let's do that. So r squared is equals to, what is our x? Our x is k, so here we have k squared, plus our y is how much? It's 1, so we have 1, right? And then from there, basically we just solve for r there. So r is going to be plus minus the square root of k squared plus 1. And then we have to choose which one is true there. So remember, we said r can never be negative. Therefore, r is equals to positive k plus 1. And r can never be negative k plus 1. See that? Beautiful, beautiful. So now we can get to the sine of 22. All set? So the sine of 22 is equals to y over r, right? What is y? Okay. What is y? Our y is 1. And what is our r? This is our r. This is our r. Beautiful, guys. Beautiful. I have no complaints there. Wait, our y is k. Look at that. Because the tangent is equals to y over x. So our y is k. So this is equals to k over k plus 1. That's the final answer. Right there. Mistake on the final answer. Not a bad way to get out. Okay guys, if you watched this video up until here, please don't forget to like and subscribe. I appreciate you for staying this long. It will definitely help you. All right. And as for me, I have to sign out. I've been here for so long. Let me check what time it is. Oh, this video is 2 hours long, but I've spent way more than 3 hours on this video because I have to do a lot of pausing, fixing my errors, resuming, and all those things. But then it's worth it. I know it's worth it. Please make sure that you watch the whole of the video. And then I know I'm saying this at the end. It's probably futile, but it's okay. I'll see you guys on the next video on part 2 of this trick series. Okay, goodbye for now. Don't forget to like, and yeah, just don't forget to like.